Hello students, welcome back to my channel. Today we will study the topics of ring theory, that is, if R is a ring without zero divisors such that a raised to power n is equal to b raised to power n and a raised to power m is equal to b raised to power m for m and n relatively prime integers, then it implies a is equal to b. And second, which we will do is we will find the field of quotients of Gaussian integers. Now let's get started.
As we have done in the previous problem that we have taken D as an integral domain. Here we will take R, a ring without zero divisors. Basically जो इंटीग्रल डोमेन की एक प्रॉपर्टी होती है मेन वो होनी चाहिए इसके अंदर. A and B belongs to R such that a raised to power n is equal to b raised to power n and a raised to power m is equal to b raised to power m for n and m relatively prime integers, that is their GCD is 1, it implies a is equal to b. Now similarly इसको prove करने के लिए first we will assume the case when a is equal to 0 and b is equal to 0, and there we will arrive that b is equal to 0 and a is equal to 0 respectively as we have done earlier. Hence we will assume that a is not equal to 0 and b is not equal to 0. Since m and n are relatively prime, there exist integers x and y belonging to z such that mx plus ny is equal to 1. अब इसमें both x and y both cannot be positive, neither both can together be negative. So one of them must be negative और हम assume करते हैं that y is negative and minus of y is equal to t, where t is greater than 0, right? So a raised to power mx is equal to a raised to power 1 minus ny, which in turn implies a into a raised to power minus y raised to power n, which in turn implies a raised to power a t n, that is a into an raised to power t. An is equal to bn, we have been given a b raised to power n raised to power t, which is equal to a b n t. एंड यहाँ पे हमें a raised to power m क्या दे रखा होता है, b raised to power m raised to power x, that is b raised to power mx. Now we will multiply with b on both the sides, which would imply b mx plus 1 is equal to a b raised to power nt plus 1. nt plus 1 हमारे पास क्या आएगा basically a raised to power b mx, which in turn implies a minus b, take b raised to power mx common, is equal to 0. And since we are with in a ring without any zero divisors, so as b is not equal to 0, it implies a minus b is equal to 0, b raised to power mx not equal to 0, which in turn implies a is equal to b. Now we will do another example which states us that find how to find field of quotients. Field of quotients of an integral domain Z Gaussian integers, basically a plus b iota, where a and b belongs to integers. So इसका solution देखने के लिए what we will do, f कैसे define करते हैं हम, if f is the field of quotients of this integral domain. So f is defined by d1 over d2, इसकी common notation use किया मैंने, such that d1 and d2 belongs to z of iota and d2 is not equal to 0, which in turn implies f is equal to a plus b iota over c plus d iota, such that A, comma B, comma C, comma D belongs to integers and C plus iota D is not equal to 0. Now, which in turn implies that if I rationalize it, multiplying by C minus D iota and dividing by it also, ये as it is same रहेगा, which in turn implies A C plus BD over C square plus D square plus iota BC minus AD over C square plus D square such that A, B, C and D belongs to integers, which in turn implies x plus iota y for x and y belonging to Q, a rational, or we can say that it is a subset. F is a subset of this x plus iota y. इसको हम assume कर लेते हैं set A. Now, if x plus iota y belongs to A, B, any element, then x and y belongs to rationals. That is, x plus iota y is equal to p1 over q1 plus p2 over q2 iota for p1, p2, q1, q2 belonging to integers, so that q1 is not equal to 0 and q2 is not equal to 0. So, in this case, we have that p1 q2 plus p2 q1 iota over q1 q2 plus iota dot, which is equal to e1 over e2, where e1 is this quantity and e2 is this quantity, such that e1 and e2 belongs to z iota with q1 q2 not equal to 0, that is e2 is not equal to 0. Since q1 q2 is not equal to 0 and we are in an integral domain, there is an integral domain, therefore q1 q2 is also not equal to 0. Hence, it implies x plus iota y belongs to, because x plus iota y can be written in the form e1 is upon e2, where e1 and e2 are elements of Gaussian integers and e2 is not equal to 0, therefore it belongs to its field of quotients, and hence it implies A is a subset of F. और ऊपर वाली कंडीशन से हमें क्या पता लगा था, that F is a subset of A, and therefore we come to the conclusion that A is equal to F. Therefore, field of quotients of Gaussian integers is equal to x plus iota y for x and y belonging to rationals is the field of quotients of Gaussian integers. In fact, अगर हम एक मैप देखते हैं, mapping phi from z of iota to f a basically, such that phi of a plus iota b is equal to a plus iota b is the embedding. A ले लो यहाँ पे या F ले लो, it's the one and the same thing. It's the embedding. Map it can be easily proved that it is 1-1 homomorphism, being an identity map. कुछ exercises हैं basically for you people to solve them. Exercises. First example of an embedding map in which unity is not mapped to unity. Second, show that field of reals can be embedded, basically a map show करना है, which is one and homomorphism from reals to complex into the field of complex numbers. Third question, find field of quotients of an integral domain Z under root 2. Its elements are a, b under root 2, where a and b belongs to integers. Fourth question, show field of quotients of finite integral domain is integral domain itself. For hint of first question, consider an embedding map phi, which can be easily shown by you that it is an embedding map on one homomorphism from Z to Z cross Z such that phi of R is equal to R comma 0, then phi of 1 is equal to 1 comma 0, which is not equal to 0, unity 1 comma 1, unity of Z cross Z. Thank you.